I should. Okay, so I want to motivate this starting from PDE. So so using the method of separation of variable, one is one of the most powerful and common methods in linear partial differential equation, right? And is actually the very beginning of development in functional analysis, like the spectral theorem, right? So let's just start from the very beginning, right? So if you have the heap equation in a one-dimensional row of length L, right? With boundary conditions, you maintain the extreme at zero temperature, and you have a certain distribution of temperature at the beginning. You want to know how the flow of heat will continue, right? For any t bigger than 0. And for that, well, it looks like a very innocent thing. Well, you say, let's assume that the solution can be written as the product of two functions, one depending only on x and one depending only on t. And then just plugging into this equation, we get two ordinary differential equations, one for g, that is dependent on time, and one for x. And yes, these conditions depend on x only, and this is what is called what is the name? Boundary value problem, right? Thank you. Then, doing that, when you try to put everything together, you are forced to ask that the initial condition, the distribution of temperature, has to be written in this form. And since you can prove orthogonality here, then you get these coefficients, right? And of course, this was, since the very beginning, very problematic, because big people like Laplace and asked, well, which functions can be represented in this form? How do you know that your function can be represented in this form? And if you change the boundary condition, so you get a sign, you need a sign representation of f for that problem. If instead of maintaining the extreme at 0 temperature, you insulate the extreme, that is, there are no flow through the extreme, well, then you get, by analogous argument, you get that the function needs to be represented in this form. That is a cosine series. And additionally, if you have a circular ring thing, and you have conditions, I mean, at the extreme, that is where you put together, has to be continuous, so the temperature at L and minus L has to be 0, and the flow between L and minus L also, you assume that is 0. And the initial condition, then in that case you get a full Fourier transform, Fourier series, sine and cosine series, with, by orthogonality, in that range negative L, you get the coefficients in this form. Okay. Not only that, but if you consider, for instance, Laplace equation and also the vibrating string, you get to a certain point that you need your boundary, your initial value, to be represented as Fourier series. So then the problem of Fourier convergence arises, right, naturally, and And actually, Fourier introduced his paper at the Academy in 1807 and was rejected, among others, by Poisson. But Poisson got a paper about Fourier series in 1820, but the proof for the convergence was wrong. Fourier tried to supply a proof in his book that is published in 1822 or something like that, and then he has he realized that there are problems in his proof. Cauchy also tried to prove it, also with certain errors. And then finally in 1829 is that Gustave Lejeune Dirichlet get a proof, which is essentially what we can get in for instance, in a PDA book, that is a function that is piecewise continuous with derivative piecewise continuous. Initially, he asked for monotonic on a closed interval. He tried to improve that, but it was not. He was not successful for that. Then I mean, his mentor was Fourier, so he really paid attention to his. Then, in the early 1850s, Riemann, a young protege by Dirichlet and a student of Gauss, made substantial progress extending the understanding of trigonometric series. So, over the next 50 years, the question will appear over and over again. So this is the beginning of analysis, because that was not only the problem of convergence, but the problem, what is the meaning of convergence of a series, what is the definition of function, and you name it, right? So all what we call now analysis was just a reformulation of what was known up to that time of calculus, right? And then something that was clear is that the nature of the integration was crucial, right? So it became clear that the Riemann integral should be replaced for something else, because the something more flexible, precisely because you need to deal with limiting process. So important names besides Lebesgue are Hilbert, Feuillère, Marcel Ries, Sigmund, and Calderon. Okay, so this is like a general framework. So let's go to more technical stuff. So we consider, if we consider the complex approach, which is considering the trigonometric system using the Euler formula, that is easy to check. That is an orthogonal system, and this is called the complex form for the trigonometric system. It's not orthonormal, so you need to normalize by 2 pi, but that's not really an issue. And then, yes, if you take a function in L1, you can define the Fourier coefficient with respect to this system. And we have the association of f with the Fourier series. And this symbol means that we really don't know in which sense these series represent the function most of the time. Okay, so if we consider the partial sums, the trick of the partial sum is that since you have a finite sum, you replace the coefficient by this representation, and then you can flip, because this is a finite sum, And then, well, you call this guy the kernel, and this kernel can be written in this form, and it's the Dirichlet kernel. And here are some graph generated in mathematics for n equal 5, 10, and 20. And as you can see, one immediate property is that the Dirichlet kernel is not positive. Oscillate is kind of localized, but at the end of the day is not good. Unfortunately, or fortunately, because of the fact that the Dirichlet kernel has not the best properties, a lot of research was done starting immediately after that. But in 1876, Dubois-Reymond obtained a result that was a breaking point in the development of Fourier analysis, which is that up to that point, even nobody was able to prove, but people suspected that a continuous function should have a nice Fourier representation. But he proved that he could find a function, a continuous function, that at least in one point diverges. And that was, an earthquake. So for over 30 years, people there was not much of advance in Fourier series. You have to wait until the development of Lebesgue measure and then the work of Fourier on summability. Okay. Then other notions of convergence were needed, as we mentioned before. The first one was the square mean, and from there the Hilbert space theory was developed. Of course, people were most of the time working with continuous function between negative pi and pi, but following Frederick Ries recognized that this setting was not the most convenient because the continuous functions was not complete. So you need to go to L2, even though they contain many discontinuous functions, but it's complete. So, but on the other hand, here there is a type of this should be minus pi pi. There is the set of Riemann integrable functions is not complete either. So that was another reason why you need something else. So it was the Henry Lebesgue theory, and then the L1 and L2 in the Lebesgue sense, not in the Riemann sense. Okay, now the L2 theory was very nice because, as you may remember, whenever you have an orthogonal system, you have the Bessel inequality. That is true for any orthogonal system, for any n, and therefore then this is uniformly bounded. Then the whole series is bounded by the norm of F. So all the partial sums are bounded, and therefore the series is bounded by the norm of L2. But then it can be proved that the trigonometric system is complete. And complete, which you may, for instance, this is a usual definition, that if you have a function that is with respect to the system equal to 0, implies that the function has to be 0, is equivalent to the Parseval identity, which is that this is not only less or equal, but equal. And using that immediately gives you the convergence that you need, that the partial sum in this norm converge to 0. Okay. Now, so this is the basis for the proof of convergence of the partial sum. Then is the orthogonality of the trigonometric system. Uh, of course, if you want to generalize for p different from 2, you want to prove that this is also true, well, then you are in a problem, because we are changing from a Hilbert space to a Banach space, right? And doing that, then you lose the geometry of the Hilbert space, the geometry of the internal product, the orthogonality, and all that, right? So in order to prove that, several tools developed in what is known now as the harmonic analysis, right? Especially maximal functions and singular integral. And let me say something about that. Using a well-known theorem in functional analysis, it can be proved that in order to prove that this is tending to 0, is enough to prove that the partial sums are bounded by the LP norm of the partial sums are bounded a constant time the norm of f, which means that the partial sums is a bounded operator in the LP space. But remember that the Dirichlet kernel is bad, so in order to improve a little bit the Dirichlet kernel, you don't work directly with the partial sum, but with the average of partial sums. Okay? And when you do that, then you have the average of the Dirichlet kernels, right? And that can be written in this form. Oh, here I should have changed this. Well, I will do it later. So, see, it's better. I mean, if here, I mean, this is a convolution, right? So here, if I put t here, then here and here I have to put x minus t. And then, using the addition formula for the sign, you are going to get two integrals, right? And then the problem is, what is this, how you can control the integral that you have there. The problem with these integrals is that you are taking a convolution of this function, for instance, ft cosine of nt or ft sine of nt, with respect to 1 over 2 tangent of x minus t, 1 over 1/2 of x minus t. So it's a convolution with respect to a kernel that, of course, at 0, the tangent is 0, so there is a huge indeterminacy here. So you are convoluting with a kernel that is not a nice integrable kernel. And that is the beginning of the need of the conjugated function. You need to understand this guy. And this is what is called the conjugated function, which was the first singular integral that appears. Right? And you need, if you want to prove the LP, you need to prove that this guy is LP bounded. If you can do that, then you can control this function and this function. This is bounded by 1, so bingo. So if you assume this inequality from this representation immediately, you get that this partial average partial sums are bounded in LP, and then it's easy to, this is an easy inequality. You get that the partial sums are bounded in LP, and therefore that implies that that the partial sums tend to F in LP. But of course, proving this is not an easy task. The first proof was given by Marcel Ries in 1827 using complex methods, and later was obtained using real method developed by Calderon and Sigma. Since, as I said, 1 over 2 tangent of x over 2 blows up at 0, And actually that discontinuity is pretty similar to 1 over x. So you can, this is the conjugated function, or sometimes it's called the Hilbert transform at the periodic Hilbert transform. Well, if you replace this guy by 1 over x and take the convolution, well, the Hilbert transform on the real line is this one. And from there, if you want to go to RDE, well, then you consider the Riesz transform, which are this guy. Oh, there is a problem here. And from there, you can go all the way up to 1953, that Calderon and Sigmund gave a whole theory about singular integrals in Rn. So, as I said, all this theory was developed because of the fact that the partial sum has a kernel which is singular. That implies a singularity, and then implies a singular integral. Okay. So we want to try to see what is going on in the case of classical orthogonal polynomials. Right? So similarly to the motivation that I gave, it's well known, for instance, that the Laplace equation on the sphere involves Legendre series, the wave equation of the linear oscillator involves Hermite series, the wave equation of the hydrogen atom involves Legendre series. So, and this is a crash course in orthogonal polynomials. If we take monic polynomial of degree n, orthogonality is equivalent that the polynomial of degree n is orthogonal with respect to x to the k, with respect to the measure for any k less or equal than n. That is 0, 1, 2, up to n minus 1. If Qn, the Jacobi polynomials are, this is what is called the Jacobi measure, and in particular, if alpha and beta are equal, you get this guy. Legendre is when the alpha and beta are equal to 0. Chebyshev of type 1 is when alpha and beta is a particular case of Gegenbauer, alpha beta equal to -1. Chebyshev 2 is alpha beta with respect to alpha beta equal to 1. And then we have Laguerre, which is interval, the delta is 0 infinity, and the measure is x to the alpha e to the minus x dx, and Hermite is the whole real line and the Gaussian measure. Okay, so there are good news and bad news about convergence of the orthogonal expansion for classical polynomials. The L2 convergence in this case is true for the three families, following the same idea that you have for trigonometric polynomial, which is you need to prove that those systems are complete. For instance, it can be proved, is a theorem in Atsego's book, which is the Bible in orthogonal polynomial, that the Jacobi polynomial, the whole family of Jacobi polynomials, is complete in L2 of -1, 1 with respect to the Jacobi measure, and that, of course, implies in particular that for all these guys the same is true. So the Laguerre polynomials are also complete in 0 infinity with respect to the Laguerre measure, and in the same result in Sego, we have that we can prove that the Hermite polynomials are complete. And here, well, the way that is proved is using the link of this problem with what is called the moment problem. That is that this knowing, the moment problem is knowing all the powers of a given measure, whether this moment determine the measure. So that's when that happens, which is true in the case of the Gaussian measure, you say that the moment problem is determined. So then, yes, we have L2 for everybody without just using the structure of the Hilbert space structure. Now, what about LP? Well, in LP, since it's a good news, you could say, right? This was a study at the end of the 1940s, between 1946 and 1949, by Harry Pollard. He studied first the legendary case, which is between -1 and 1 dx, the Lebesgue measure, right? No weight. And then he studied the Bauer polynomial, and finally he studied in full generality the Jacobi polynomial. Actually, he got even further than Jacobi polynomial, but we don't want to get up to that point. So of course, for that, well, you define the Banach space LP between -1 and 1 with respect to the Jacobi measure. You have the LP norm with respect to that. And then, yes, it can be proved that, well, still, you know that from what we discussed previously, that, yes, the polynomials are orthogonal in LP. Okay, in L2, sorry, I mean with the internal product. You can still use that product, but that will not help that much. And especially since you see from the experience that you have from the Fourier series, you are not expecting that the orthogonality will be crucial in any sense in this case either. Okay, so of course, Jacobi polynomials can be also obtained not just as an orthogonal family, but as solution of the Jacobi differential equation. And this, taking this guy to the other side, tells you that the Jacobi polynomial also can be obtained as the eigenfunctions of the second order diffusion operator L alpha beta, which is the first part, this part of the equation. Which is what is called the Jacobi differential operator. Okay, so what do we do? Well, we consider again trying to do the same as in the case of the Fourier series. You define the Fourier coefficient. Again, this is not an orthonormal basis, but then you use you normalize it with the value of Hn, which is this guy, right? The L2, the square of the L2 norm, if you wish. And then define the partial sums. And what you want is to see if you can say something with a similar trick that you did in the case of the Fourier series. Well, doing this exactly the same trick, you replace the Fourier Jacobi coefficient here, and yes, again, this is a final sum. You take the integral outside and put the sum inside, and then this is what you get. And the question is, what can you say in this case? Well, luckily for us, this is known. This is what is called the Dirichlet-Szego Jacobi kernel for Jacobi polynomials. And the representation, thanks to the recurrent relation, which is a very nice property of the Jacobi polynomial, you can get what is called the Christoffel-Darboux representation of this guy. And this is a constant. And not surprising, see, you get a singular kernel. You have the x minus y in the denominator. So that is not entirely unexpected because, well, the same happened for the Fourier series, right? And then yes, using that representation, we can get an integral representation of the partial sums for the Jacobi series in this form. But then the problem is then what can you do with this kernel, right? Well, so the Dirichlet-Szego kernel is a singular kernel, so yes, we are in presence of singular integral again, right? Harry Pollard proved that for alpha and beta, remember, well, I didn't mention explicitly, but alpha and beta for Jacobi polynomials must be bigger than -1. But the proof by Pollard was alpha beta bigger than -1/2. And different from what we have for Fourier series, which is that P was between 1 and infinity. Here we have P between this maximum and this minimum. He is able to prove that the partial sum converges in LP when P is in that range. Okay? And in order to prove that, what he did was to, and this is a very important decomposition, he decomposed this kernel. He decomposed this kernel in 3 parts. 2 are kind of symmetric, and this is just a product of 2 polynomials, one in x and one in y. So T2 and T3 are symmetric. You are just changing the role of x and y, but yes, they are singular. And yes, you can get that these coefficients are equal to this expression. So, well, first he was able to prove that alpha n and beta n are bounded about, but are constant depending only on alpha and beta, but not of n, which is clearly not entirely trivial. And that this decomposition has been used afterwards several times, and is what is now called the polar decomposition for the kernel, right? Okay, so again, as I mentioned in the case of the Fourier, using Banach-Steinhaus, what we need to prove is that the partial sums are bounded in LP, right? Are bounded operators. Okay. Well, this is a famous estimate that, you know, the Jacobi polynomials are bounded in this form. So with this estimate, then you can control easily this guy. But then for T2 and T3, which are the singular operators, well, in that case, guess what? Well, we need to use the continuity of the Hilbert transform that we mentioned as a generalization of a non-periodic conjugate function. Okay? Actually, this problem, not in that moment, but this moment was one of the main motivations that later Benjamin Mackenhoff and Richard Whedon, students of Sigmund, developed what is called nowadays in harmonic analysis as the AP weight, which is, we know that the Hilbert transform is LP continuous, right, or LP bounded, and the question is, if you put weights you consider LP spaces, but with weights, what are the weights that allow you to still say that the Hilbert transform can go from LP to LP. And you can see clearly that here, because we are working with this norm, that is a natural question, right? Right. So, and these are power weights, right? These are power weights, and not by chance. This was one of the first approach that Mackenhoff took. But in the case of polar, I mean, the AP weight theory is from the early 70s. Polar, we are talking about 1946, 1949, is far from there. And he succeeded to introduce the Hilbert transform and use the Hilbert transform inequality with respect to the Lebesgue measure, no weights, and the polar decomposition allow you to do that. The proof is very difficult because of that, right? But he's able to get the proof through. Additionally, he proved that you cannot go below this guy nor above this guy, so it's optimal. That's the range. So this is the only range. You cannot expect more than this range. Later, Newman, in 1952, Newman and Walter Rudin, by the way, studied the cases, the extreme cases. What happens when P is the maximum of these two guys or P is the minimum of these two guys. And in those limit points, the LP convergence fails. In particular, if alpha and beta are equal to -1/2, see, if alpha and beta are equal to -1/2, this is infinity. 2 alpha plus 1 is infinity. And 2 alpha is -1, so this is 2. And alpha plus 1 is 1/2. So we get the range 1 to infinity, which is not surprising because the Chebyshev polynomials are cosine, can be written as polynomials in cosine, right? So in that case, we recuperate the Marcel-Ries classical theorem for Fourier series. And in the case alpha beta equal to 0, which is alpha and beta equal to 0, we get the range 4/3, which is the first proof that obtained polar in 1946. Okay, actually, the paper of polar was not really, as I said, he created a general class of weights that are of this form. And his last paper is not about general Jacobi polynomial, but even further, which is this guy. And that's why that is very difficult. It's already difficult, but since he's working with a class that is even larger, it's a very difficult paper. In particular, of course, if this guy is 1, right, then of course you get the Jacobi weights. Right? And he has a famous hypothesis to prove that, and everything includes that at the end is the problem is to work with this kernel, with this operator, where the kernels are given like this. So this is a very difficult topic, but if you rewrite things just for the Jacobi, you can get it. And this is what a student of mine did back in 2003 in Venezuela. So we wrote the proof, not the general proof, but just the Jacobi polynomial to understand. Right? Okay. In 1950, Wien extended the polar resolve for Fourier Bessel expansion, and again the range for in that case was 434. And and in 1969, almost 20 years afterwards, precisely Mackenhoff gave a proof that filled the gap. Remember that the polar result was for alpha and beta bigger than -1. But the Jacobi polynomials are defined for alpha and beta strictly bigger than -1, right? And of course, he was already working in his LP, the AP theory of weights. So he actually considered more general weights that are of this form, where A and B satisfy certain conditions that are these guys, that it takes a while to see what is going on here. But the amazing thing is that when A and B are alpha over P and beta over P, those are nothing but the Jacobi weights, right? Right? So if this is 1 over P, this is A, and if B is 1 over if B is 1 over P, this is how is that? Well, alpha over P and beta over P, right? And then he established this inequality, which is a weight inequality for the Hilbert transform. So you use these guys with certain restrictions, and yes, this theorem is true for any alpha and beta bigger than -1, and yes, it includes the polar result, of course. And the proof is easier. Why? Well, because once you know this inequality, the handling, he used the polar decomposition. He used this guy. But now he can handle T1, T2, and T3 easily, because you have a power inequality, a weight inequality for the Hilbert transform, something that polar didn't have. Okay. What else? Well, there are quite a few results related to this. For instance, in 1991, a group in La Rioja worked with generalized Jacobi weights. And you can go beyond that, but we can stop here, right? And then you may ask, well, what happened in the other cases? That is, well, for Jacobi, we have already a well-established result that was finished by Mackenhoff. What happened, for instance, in the Hermite and Laguerre case? Well, that is a surprising result, right? Because if you consider the LP space with respect to the Gaussian measure, or the LP space in R, or the LP space in 0 infinity with respect to the gamma measure, you can prove that the polynomials are LP dense in those spaces. Nevertheless, already in his article in 1948, Pollard said this. This is the weight for the Gegenbauer polynomials, right? If we replace x by lambda over square root of x by over square root of lambda and take lambda tending to infinity, this weight tends to e to the minus x squared, right? And yes, then it can be proved that the corresponding polynomials are nothing but a multiple, at most a multiple of the Hermite polynomial. Therefore, but in the case of the Hermite Gegenbauer polynomials, see, if you remember where was the condition of in polar theorem, this is the alpha and beta are the same and are equal to lambda minus 1/2. Well, it's easy to check, I think I am running out of time, that in that case, these two guys that are the range for P tend to 1/2. So just looking at the bounds, it looks like well, the only possibility for Hermite polynomials is the case of only for P equal to. Not only he gave this intuition, which is very deep, and we have used that in other works. For instance, to prove that if you have the singular integral with respect to the Jacobi, you can get the result for singular integral boundedness with respect to Hermite or Laguerre using this idea. So that was a doctoral thesis of a student of mine in Venezuela. And so to make things closer to, I mean, we can skip all this. These are the Jacobi polynomial, the Gegenbauer polynomials, when alpha and beta are lambda minus 1/2. And this is a very well-known formula, which is the intuition that Polar gave in that paper, which is when lambda tends to infinity of the Gegenbauer or ultraspherical polynomial properly normalized, you get nothing but the Hermite polynomials. And he gave a counterexample. He considered this function, and he saw that function, the Hermite coefficients in the odd part of the Hermite coefficients, the odd coefficient for the Hermite polynomials are 0, and for the even coefficients are like this. And from there you can prove that this tends to infinity. This blows up. So then there is no hope for any P different from P equal to, that we already knew. I mentioned that from the fact that the moment problem is determined for the Hermite, you have L2 convergence, but there is nothing else but L2 convergence. And the Laguerre case is analogous because there is a tight relation. Hermite polynomial can be obtained from the Laguerre polynomials with a well-known formula in the case of the in the context of the orthogonal polynomial theory. So since it's bad for Hermite, at least for some Laguerre are bad too. Right? So surprisingly, even though again the polynomials are dense in LP of those spaces, the polynomials that are close to a given function are not necessarily the partial sum of their expansion. That's what this is saying. Okay, I think this is so here is a list of reference. This is it's an old book, but very nice. And here is oh, what is polar? Here is not polar. Oh, I forgot to put it. So it's a series of papers. And well, that's it. Thank you for your attention.
Very good. Thank you.
Any question or comment?
Yeah. I have one question.
Sure.
Sorry, my email got crashed and ID. So what was so you had this mu over alpha beta, that's 1 minus x to the alpha times x minus 1 to the beta, right? Is that a popular measure, like a Gaussian measure? Because I never seen that before.
Yeah, I mean that is what is called the those are measured that you see. Those are measured that live between -1 and 1 because and in the space in the extreme they have singularities. So yes, those are well-known measures in the
Okay.
of this class of polynomial.
Is there like a specific name, or is it derived from beta function?
Jacobi measures, right? And you know, if you think about it, if these measures are um, well, you could say, well, since you have singularities near here, this will blows up when x is near 1, and this blows up when x is near negative.
Okay.
And one of the reasons that this is bigger than -1 is because that can be controlled, right? And if you think about it, I mean, by a change of variable, and see, for instance, I mentioned that when you see this this bunch of gammas and the constant appear naturally, you can rewrite that because the measure is related with the beta function. When you make a change of variable, you see that actually the measure is a beta function. So and then the total measure is the beta function in alpha beta. Yeah, but
Thank
yeah,
you.
these are kind of weird measures, but I mean they contain, as you can see here, there is a whole family. This is the largest family of orthogonal polynomials, right? And in particular, for this measure, you can see that these are the cosines, which is crazy. So, in a sense, then therefore the theorem, the polar theorem, includes not all but part of the Fourier analysis because include the cosine series. Yes. Okay. Any other question? I will stop